In this video, we're going to be introducing the concept of thermochemistry. Now, thermochemistry, as you can probably determine just by looking at the name, has something to do with heat and something to do with chemistry. In fact, what we're talking about is the heat that is either released or absorbed during the course of a chemical reaction. Now, in some reactions, we have some reactant producing some product along with heat. Okay, these are reactions that are warm to the touch. Okay, and we call these reactions exothermic. Okay, because they are giving off heat. There are other reactions that will not proceed unless you apply heat to them. Okay, so the heat is being consumed along with the reactants to produce the product. And this type of reaction we call endothermic. Okay, now how do we explain this? Well, in order to truly understand why these two types of processes happen, we need to understand a basic principle of the universe that we call the First Law of Thermodynamics. And what this law tells us is that energy is neither created nor destroyed. Okay, so overall what this is telling us is that energy can change forms. Okay, but it can't just simply go away. But what does this have to do with these reactions that I just showed you? Well, let's take a look at an energy diagram for each of these reactions. Okay, when we look at the amount of energy that is stored in the bonds of chemical A. Okay, for this type of reaction, the energy that's in chemical A is greater than the energy in chemical B. Okay, so that means that in the course of this reaction, as we go from A to B, we are going down in energy, or we're decreasing the amount of energy that's there. Okay, so what happens to that energy that is lost? Well, it has to be given off somehow. It can't just disappear. Okay, so that has to be given off as heat. Okay, now for the endothermic reaction, we have a similar situation. Okay, but now we're looking at a case where chemical A is lower in energy than chemical B. Okay, by the way, these aren't the same reaction, obviously, because you can't have one reaction be both exothermic and endothermic. Okay, but in order for us to go from A to B, we have to increase in energy. Okay, so going from the reactants, okay, and the amount of energy that's stored in their bonds, all the way up to the energy of the products and the energy stored in their bonds. Okay, we are increasing the energy, and the energy again has to come from somewhere. Okay, again, we can steal heat. Okay, so for an exothermic reaction, we have heat that is leaving, and for an endothermic reaction, we have heat that is coming in. Now, I keep using these terms in and out to describe the movement of heat. It'd be much more scientific if we had some vocabulary that we could use. Okay, so when we're talking about a chemical reaction takes place inside of a flask. Okay, so perhaps a beaker. Okay, so that beaker is going to be probably filled with some kind of a solution with reactants in it that get converted to products. Okay, and one of two things is going to happen. If it's exothermic, the heat that is inside the liquid is going to leave, okay? Whereas if it was an endothermic reaction, the heat that was outside of the flask makes its way into it. Okay, so the way we define things is that this area of interest, this place where the reaction's taking place, we define as the system. Okay, everything else is the surroundings. Okay, so you have your system, you have your surroundings. So if I have an exothermic reaction, okay, heat is lost to the surroundings. So the heat's going from the system to the surroundings. If I have an endothermic reaction, heat is flowing from the surroundings into the system. Okay, and probably the most important thing to realize here is that the energy, well, I'm sorry, that the system plus the surroundings composes the entire universe. Okay. Now, when we take this in conjunction with our first law of thermodynamics, okay, this starts to reveal a lot of information about how we can predict where heat is going to travel to and from. Okay, so if you think about it, if there's only two parts of the entire universe, the system and the surroundings, and we're interested in the transfer of heat from the system to the surroundings, what this tells us is that heat in the form of, or energy in the form of heat, can be only in one of two places. Okay, so in other words, if I had $5, I could hand it to you, okay, and transfer it to you. But in principle, in the real world, I could have dropped it while giving it to you. Okay, there is no dropping the energy when we're talking about thermochemistry. Okay, the energy is either going to be one place or another, either in the system or the surroundings. A good example of this would be if you were to consider a cup of coffee. Okay, so imagine one of those styrofoam cups, and let's say that we just filled that up with red hot coffee. Okay, so we got steam coming off here, and you decide that you're going to take this coffee and you're going to let it sit on the table for a couple hours. Okay, now we all know that that coffee will not be as piping hot when you go to see it or go to taste it in a couple hours as it is when you first started. Okay, that's because heat is being released. Okay, so the coffee is losing heat. Okay, but if it's losing heat, it has to be going somewhere else. And the only place that it can go would be to its surroundings. So in this particular case, the coffee, okay, which is our system, is losing heat to the rest of the room, okay, which is our surroundings. Now, I've simplified that a little bit because the surroundings really is going to include the room, the building, the planet, the universe. Okay? So if you think about it, as the temperature of the coffee decreases, Okay, so as the temperature of the system decreases, the temperature of the surroundings is going to increase. Okay, so that cup of coffee that you set on the countertop for a couple of hours, having lost its energy, okay, having given off its heat, has actually warmed up the room. Now, you're not going to be able to detect that increase in temperature because there's a lot more matter in that room than there is in that little coffee cup. But that is, in fact, what has happened. Okay, now, this is a nice qualitative approach to understanding thermochemistry. But what about the quantitative work? How do we deal with numbers here? How do we start building equations? Well, let's go back to our first law of thermodynamics. That tells us that energy cannot be created nor destroyed. If it's not created nor destroyed, that means that the amount of energy that we have in our universe right now is the same as the amount of energy that we had when it first started, and the same as we will have forever, or however long the universe lasts. Okay, think about that. That means that we can write an equation that looks like this. Okay, the change in the energy of the universe is equal to 0. Okay? Okay, and we know that any change that, if it were to occur in the energy of the universe, could only happen if we had change in the energy of the system and or change in the energy of the surroundings. Okay, which tells us if the energy change in the system plus the energy change in the surroundings gives us the energy change in the universe, and the energy change in the universe equals 0, that means the sum of these two values must also be equal to 0. Okay, now let's take this one step further. What this tells us is that if there's any change in the energy of the system, it must be equal to the negative of the energy change in the surroundings. Okay, isn't that exactly what we just talked about with this cup of coffee? Okay, so the coffee is losing energy. However many joules or calories of energy that it's losing is equal to the amount of energy that the surroundings are gaining. Okay, the difference between the two is simply the sign. Okay. Now, for a moment, let's simplify things a little bit. When you think about it, we certainly cannot calculate the energy in the universe, and we certainly cannot calculate the energy in the surroundings, because the surroundings include the rest of the universe. But we can calculate the amount of energy within a given system. So we're going to focus on that. Okay, so we're going to rewrite this now. Instead of using delta E of the system, we're just going to say delta E. Okay, and we're going to assume from here on out that if I just put that delta E there, that we're just talking about the system itself. Okay, it's a lot easier to make measurements inside of a coffee cup than it is to make measurements that span the entire universe, which I'm sure you can understand that. Now, let's think more about this. How can the energy of the system change? Well, it can only be exchanged if there is a transfer of that energy with the surroundings. How can we have energy be transferred? Okay, and for our purposes, any changes in energy are going to be due to one of two processes. Okay, the first one is the loss of heat or the gaining of heat. Okay, the other possibility is by having work done on or by the system. Okay, now looking at work being done by a system might be a little bit unusual at this point for you. We're used to seeing work, if we've taken any kind of a physical science or physics class, described as a force that's applied over a distance. Well, the molecules that make up a system are not always going to be aligned in a particular direction, working in concert to cause something to move, okay, or to push something. Instead, what we focus on is called pressure volume work. Okay, or PV work for short. Okay, and in pressure volume work, we're kind of going back to our discussions of the gas laws, that we can cause a gas to expand or to compress by changing different properties. Okay, and when we're talking about pressure volume work, that work is defined as being negative of the pressure times the change in volume. Okay, so a more graphical representation of this would be if you were to consider having a piston inside of a cylinder. Okay, and we have a plunger here. Okay, that's attached to a rod. Okay, and we have gas particles that are inside of this region here. And of course, these gas particles are acting like gases do. They're bouncing all over the place, from off of each one of the walls, off of each other. Okay. Now, if we were to change something inside of that container, okay, to increase the pressure inside of the container, what we're going to do is we're going to wind up pushing against that plunger and pushing out this piston. Okay, so anything that causes the gases to expand, okay, is going to lead to work being done on the surroundings by the system. Okay, alternatively, if the surroundings were to increase their pressure and push back in onto that piston, okay, through a process called compression, okay, what we're going to see is that the piston is going to be pushed down and the particles of the gas are going to be pushed closer together. Okay, and in this case, we are saying that work is being done on the system by the surroundings. Okay. All right, so again, that's just a little aside there. Now let's look at what kind of an effect this expansion or compression is going to have on the energy of a system. Okay, so if a process is taking place, that is, say, exothermic. Okay, that means energy is being released from the system in the form of heat. If energy is leaving the system, okay, that means that the change in energy is going to be equal to a negative value. Okay, in an endothermic process, okay, this is where we have heat that is being pulled into the system, we are increasing the energy of the system. So the change in energy is going to be a positive value. Okay. Now, if we have a system that is undergoing expansion, okay, think about what that's going to do to the energy of the system. If it's expanding against its surroundings, it must be exerting energy. It must be giving up energy somehow. So the change in energy there is going to be a negative value. Okay, and if the system is undergoing compression, okay, the molecules that were kind of just hanging around before are being squeezed together. That's giving them more energy. So the change in energy there will be positive. Okay, now let's relate these qualitative terms to the energy that's associated with the heat or the work. So in an exothermic reaction, heat is being released. Okay, we are going from high energy to low energy. Okay, so that means for an exothermic reaction, the amount of heat that is being lost is going to be a negative value. For an endothermic reaction, okay, heat is being gained, so it's going to have a positive value. Okay, now when we have expansion, think about what's happening. Okay, when we have expansion, we are talking about the volume increasing. So that's a positive value. Okay, but when we come back to this equation up here, okay, you can see that delta V, when it's positive, multiplied by pressure, which is always positive, multiplied by a negative, will be negative. Okay, so when we have expansion, work is a negative value. Okay, and then if we have compression, then the change in volume is going to be negative. Okay, and in that case, work will be positive. Okay, so if we think about the total energy of a system, if we have a reaction that is exothermic, okay, and is undergoing expansion, okay, that's a negative value plus a negative value. Okay, we are seeing a decrease in energy. So delta E is a negative value. However, if the reaction was endothermic, okay, and it's being compressed, okay, both of those terms now being positive values are going to give us a change in energy that is positive. Now there's other possible scenarios, right? We could have an exothermic reaction where things are being compressed, or an endothermic reaction where things are allowed to expand. In those cases, it's just going to matter what the magnitude of each one of the terms is. But we can use this equation right here to calculate what that actual value is going to be. Okay. Now, while it's helpful to be able to measure the amount of energy that's changing hands in the course of a process, just measuring energy is not something that's easy to do. it would be nice if we can somehow relate this change in energy to a term that we could actually measure experimentally. Okay, and in the next video, we're going to introduce that term.